Welcome to in-depth lectures on climate change studies. Today, I'm going to talk about emissivity and absorptivity. But in the meantime, I will also refer to some of the mistakes happened in the climate change studies whenever they refer to Kirchhoff's laws. Okay, let's start. So emissivity and absorptivity are two basic parameters frequently used in the thermal radiation in the study of thermal radiation. So in many cases, in the textbook, in the published paper, you will see people simply say, according to Kirchhoff's law, the emissivity epsilon were equal to absorptivity. Can we see it? Can we call A? Or sometimes we call alpha, or sometimes A, doesn't matter. So that is what they call the Kirchhoff's law. But I mentioned before that Kirchhoff's law didn't say so. Kirchhoff's own, if you compare with that original Kirchhoff's law, that Kirchhoff's law said the emitted energy, the ratio of emitted energy over absorption were equal to function, or what he believes is a universal, is general function, universality. And can we just record this as F, which would be the function of the T. Okay. And in some textbooks, they write the lambda, but I don't think so. And because when you measure the radiation distribution, how do I say that? And that primarily it is a function of T, okay, of T. Unless, of course, if you study different colors, then you will get that if you put this lambda here to indicate you can measure at a particular wavelength, around particular wavelengths, and that will become the function of both T and lambda. Okay, that's trivial. So my point here is that this claim is incorrect. Okay, because originally Kirchhoff didn't say that proportionality is unit. Okay, unit, unless this proportionality is unit, and otherwise we cannot make this claim. On the other hand, we also frequently see that when we refer to the Stephen Boltzmann law, we use intensity equal to this parameter called emissivity, multiply the sigma and T to the power of 4. So today I'm going to talk about these two equations in relation to the basic assumptions and basic formulas to be discussed. So by definition, so where does this emissivity and absorptivity come from? Perhaps we still need to refer to that diagram we used before. So if you have some absorbers here, one-dimensional absorber, and if you just draw the x-axis as the thickness, and this vertical one will be the intensity. Okay, so in this case, and of course, as we discussed before, this would be the L, this would be the X. So after absorbed the external radiation, so the absorber itself became radiative. Okay, so in addition to the transmitted radiation from the external source, and I use this slightly different color to indicate that the material itself also originated from inside, of course, measured at the surface, but accumulate. I recently redefined this concept that is thermal radiation as accumulated radiation. So that is the accumulated forward radiation. This is what we call the accumulated backward radiation. So in the case if the absorber became the source, a secondary source of radiation, and then we have to take that accumulated radiation into account. Here we have to emphasize, I just label that. So this one will represent external, and that is transmitted. So this would be the external transmitted. But this, if you consider it a resultant, then we don't have to put this subscript. I simply written that is air to indicate that the overall radiation one can measure it at the end of this, at the position L. Okay. So in general, as we discussed before, that emission is made by, so if we just work out, if we want to work out emission, then we have to use, we have to rely on the Planck function, remember? So that the emission can be calculated by using the Planck function, U lambda T, for black body. And realizing that there's no real object which can be treated as an ideal black body. So black body is the ideal model, like ideal gas. One can never achieve, we can never be able to find that a real object. Okay. So therefore, we have multiplied the constant here. We have to scale the spectra. So that is how we introduce epsilon lambda here. And bear in mind, this epsilon lambda is also, in general, is a function of time, of wavelength. So in other words, we just, so this is spectra, so we have to integrate that. We have to integrate them. So we have integrate them. In this case, we have to, from 0 to infinity, that d lambda. So what does this equation graphically mean? Is that if you haven't studied Planck's law of thermal radiation, Planck radiation, I will draw this graph here. So basically, if you have this Planck radiation law, in this case, governing the radiation of this secondary source, or meaning the absorber. In this case, that is U, this is U, lambda T, and this is lambda. So that graph would be, looks like this at a given temperature, of course. So the distribution, the profile is similar, but the detail is determined on the temperature. Now, in this case, in real case, that because they compare with the black body, and the percentage of the radiated energy is also smaller than the black body. So therefore, we have to consider this would be our case. So we have to take some discount. This is just hypothetical. It could be in a real case that function could be much more complicated. So in this diagram, so that will represent a Planck function, U lambda to lambda T, and this yellow one will represent that the product. So that would be represented. So this also is called the black body of the black body, and that yellow one will correspond to the gray body. Gray body means that not 100% energy absorbed can be re-emitted. Gray body. So that is expression for the emission, in all direction. Of course, these were equal to, that were equal to the sum of forward plus backward for this one-dimensional process. And how about absorption? On the other hand, by definition, absorption will be measured as supported, because absorption is driven by the external radiation. So therefore, in general, we have to put this IEX. Whenever I write this bracket, which means that I'm talking about the spectra. So actually, so if you use a spectrometer here, you can actually see the distribution, the similar distribution. So they also, this is kind of similar to the Maxwell-Planck's law of black radiation. So that is a lambda. So you can see that if you, whenever you see this use a bracket, I mean that is a spectra. So you integrate that for the whole over the area in order to calculate that absorption. So normally we have put the constant here or coefficient here, which called the lambda, alpha lambda. Can you see? So by the same token, so this alpha lambda can be not necessarily constant. Okay, actually, in recent study, I noticed that we should go to beyond the infrared, go to far infrared toward the microwave region, and emissivity. It's called the spectral emissivity. So whenever you see the spectra, the lambda here, they have proper adjective to add it. So that's one called the spectra emissivity. And this same way, in the same way, it's called the spectra absorptivity. Or sometimes you can call it absorbance, very close idea. So, but the absorbance is referred to the overall, not specific. Just stick with the absorptivity. It's more reasonable definition. Okay. So you can, after this integration, can you see this is a definition of the absorption and emission. Okay. And apparently, if you just divide them, you can hardly assume that they are equal. The ratio is equal to their to unit. Okay. Actually, in order to get something similar to the to this general claim here, we must introduce what we call the mean absorptive. So that is a new concept I redefined recently. So this is called the mean, like a statistical mean, as a mean emissivity. Actually, every emissivity here can be considered as a mean. So the mean emissivity. So by definition, the mean emissivity can be written as integral. So one is from 0, the integral emissivity, spectral emissivity, multiply Planck function, that is u lambda t d lambda from 0 to infinity, divided by divided by this integral. You can consider this as a normalization condition. That is u lambda t d lambda. Do you remember? This integral give you Stephen Boltzmann's law in previous talk. Okay. So that is the mean emissivity, definition of the mean emissivity. Okay. Also, you can consider that is a relation between the general emissivity and the spectral emissivity. Similarly, we can also define the mean. Can we write down somewhere here? We can write something here. I write the same, we still have some space here. Similarly, we can write the mean of absorptivity. So that mean absorptivity can be written as integral 0 to infinity. That is alpha lambda, this is spectral absorptivity, multiply the internal spectra, external intensity, or you can call it spectra. And could be a that could be an ideal black body. So that in that case, you can apply the Max Planck's function divided by 0 infinity, and that is external spectra lambda t, d lambda and d lambda. All right. So if you take into account of what we have observed, you can see these would be the exactly black body radiation intensity. You see that's black body radiation intensity. So that will become this by definition that's our emission, the total both forward and backward, and that one we know that it is exactly equal to a constant. So that equal to the, if you do have to change to switch to the Boltzmann law, we have to multiply, we have to consider the factors. But here, perhaps I just noticed that this is the intensity. Can we just say this is the intensity? Should I say, it just, we have to use this A constant, okay, A constant. That's a T to the power 4. So it's slightly different from the formula for the Stephen Boltzmann law in the textbook, but this is relevant. It's quite relevant. For the second one, we are not sure. So we are not sure whether this source is a black body or not. Okay. So therefore, and we can just simply written as A multiply the external. So that is after integration, you got the total intensity. Total intensity. All right. So you can see. So this can you see that there is a slightly different. So if you cannot just simply use Stephen Boltzmann law here. Okay. So if you rewrite in this two formula, what do we have? So we regard that emission or radiation by the absorber were equal to the constant epsilon multiply, and there are some, I will double check that. You see there's this is A, and there's some constant missing, right? Anyway, can we just simply rewritten this, continue write this as epsilon multiple. Let's double check. I don't want to make any uncertainty in this talk. So if you do want to consider that difference, if you want to apply Stephen Boltzmann law, then A must be equal to, that's right, you can't use, can we just use A here? T to the power 4. I will fix that next time. So absorption energy, so that is, again, these will represent the radiation of black body radiation, okay, black body radiation. And can put the average sign here. And absorption were equal to alpha mean value of alpha. So this is called the mean. This is our mean absorptivity. In this case, and you can call it the absorptance. Okay, I talk about this idea. Let's just simplify this result first. So that would be equal to multiply the intensity of external, and this is very close, not exactly equal to, very close to the black body radiation. Black body radiation. So that is I will check that why this is A here. Oh, we can do that. No, that would be exactly. I realize now that is the reason. Okay, I think in this case we can simply written as Stephen Boltzmann law sigma. Okay, so you can see this is a sigma T to the power 4, because although because this gives you. So there's simple relation that we can use this simple relation that What is the simple relation? That is, oh yes. So bear in mind that the sigma, I can write it somewhere. So sigma is equal to A multiplied C divided by 4. Okay, use this simple relation. So you can multiply the factor on both sides. You can just multiply factor. Can we multiply factor here and divide the same factor here? So we can get this information. So in this way, so we have proof that what we are talking about, that this simplified assumption is not correct, right? So if you just if you, according to Kirchhoff's original idea, so if you divide E by A, okay, you cannot get unit. Okay. So therefore, in general, so this formula is incorrect. So this formula is incorrect. So that is a message you take away from this mini talk. Okay, thank you for viewing, and have a nice day, and goodbye.